All right, my name is Thomas Rodgers. I work with Red Hat, and I'm going to talk to you about some work I've been doing to get C++17 parallel algorithms supported in at least one, if not two, standard libraries. So, a brief bit of background. I'm a senior software engineer at Red Hat, like I mentioned. Recently minted standard library ELF. Apparently that's what they call library developers these days. I've been a WG21 participant since 2013, mostly in SG1. And I've spent, before Red Hat, about 22 years in the finance industry doing C++ development, basically. We'll try to hold the questions to the end. I think there'll be time enough to have a Q&A session, but I've got to hop right after this talk. So if you just want the bits, there's a link. You can go and play with what we're going to talk about today. And if you've got feedback, please send me mail. But let's go ahead and talk a little bit about algorithms and what we're doing to implement them, since we've got an hour together. So the parallel algorithms, these are new with C++17. Most of you probably have at least looked at them if you've not been able to use them because your standard library didn't support them. But the idea is that the parallel algorithms provide overloads for all the standard algorithms, and they'll take a execution policy as its first argument to distinguish them from the standard algorithms that have been there since C++98. The policy describes how these things should be executed. Currently we define a sequence policy, and parallel unsequence policy. We might be getting a vector policy in C++20 as well on top of that. So what do these policies mean? So the sequenced execution policy is sort of the moral equivalent of what you already have with the serial algorithms. Essentially, your operations are indeterminately sequenced within the calling thread. You know that when you call in the algorithm, it's going to run within the context of your thread, and it's nominally the same guarantees you would have had before the introduction of these execution policies. The one that's probably of most interest to people, and the reason for coming to this talk, is probably the parallel policy. And what this basically says is that operations may be executed in parallel, either in the calling thread or any other thread that the runtime supports or spawns to support your execution. And then there's an additional relaxing of those requirements for the par and seek policy, which allows them to be executed not only in parallel, but it gives the implementation permission to vectorize, do work stealing, migrate tasks as they're running, things like that. So it's important to remember that these execution policies are permission grants to the implementation. They're not requirements. A implementation may choose to completely ignore a request for parallelism, maybe because there's no profitable parallelism to be extracted for a particular algorithm, or maybe your input size is too small. So it's great if you want to go and see what the implementation status of this for the compiler that I work with now, GCC, you will find that they're not supported at all. So our C++17 conformance is definitely lacking in this area. But I also want to mention that GCC has had for many years a parallel mode, but this is not the same thing at all. The parallel mode only implements some of the C++98 algorithms. It does it with the OpenMP support that's already in GCC, and it's likely to end up being deprecated once we start shipping proper parallel algorithm support. So about 6 months ago, I took a job with Red Hat, and basically this was pretty much what was told to me. Great, you got a job, start working on parallel algorithms. So we've got a couple of options if we want to implement this. We could create a new one from scratch, GPL3 it, or we could try to adopt an existing implementation with a compatible license. And fortunately, Intel have offered to donate their implementation to both GCC and Clang. It's standalone, you can use it today. It's a fairly complete implementation of the C++17 standard algorithms. It doesn't vectorize or doesn't parallelize everything. It also has non-standard support for vectorization, which isn't part of the current standard. So if you want vectorization, you can turn that on with this implementation. And importantly, it's permissively licensed, so it makes it easy to have a discussion about using that implementation rather than creating our own, or easier. So great, I've got an implementation I can consider using, but there's a whole bunch of work to actually get that into the standard library because it's written as a user mode library, the way that anybody who normally works on sort of, not user mode necessarily, but sort of above the standard library layer, the way that you would tend to write code. It's written in those terms, not the way that a standard library would typically be written. So there's a bunch of work that has to be done to actually get it into a position where it could be pulled into a standard library implementation. One of the big ones is what's called uglification. Macros can basically appear anywhere, and within some limits, they can have any name, and they can replace any identifier anywhere in the implementation. So, your normal code doesn't really have to guard against this, but a standard library absolutely must. Otherwise, really bizarre things start to happen. So, in order to enable this, C++ reserves any name in covered by lex.name, and importantly for the work here, anything that contains a double underscore or begins with an underscore followed by an uppercase letter is reserved by the implementation. So you end up taking reasonable, readable code like this and then doing this to it everywhere. And so that's a big chunk of kind of just the tedium of getting this into a position where you can even begin to use it in the standard library. Another issue is ADL. If you have non-namespace qualified names, those are subject to argument-dependent lookup. So in this example, which pattern walk would actually end up getting called here? You don't know. You hope it's yours, but it could be somebody else's. So you have to be deliberate about which namespace you're talking about, the context of identifiers that you want to, functions that you want to call, by explicitly qualifying them like this. You may not have to concern yourself with this in your code because you don't have a lot of accidental name collisions, but in the standard, we have to guard against this everywhere. Internal. Is it? Yes. All right. Okay. So it could potentially substitute through for internal here as well. Good point, Marshall. Although it turns out standard library actually reserves internal. So, woohoo! Happy accident. Yeah, so, in general, Marshall's right. I would have to double underscore the internal if it was not reserved by the standard, but accidentally it happens to be, I guess. So, in this case, I found that out very much after the fact. So another issue here is, and Microsoft actually found this out pretty early on, that you pull in your nice parallel implementation. It's not small, there's a lot of code there. And then anybody that used algorithm, numeric, or memory before starts seeing significant compile time regressions. Because even if you don't use the code, you have to parse all of those template expansions, and that takes time. So this was arguably not the best decision by WG21 to just lump these into the existing headers, but that ship sailed, and so I've now modified the implementation so that you only actually get the implementation of these algorithms if you include execution, because you can't specify parallel execution unless you have a policy to pass. You don't get the policies unless you pull in the execution header. And I believe that Microsoft's implementation does something very similar to this as well. So testing is the other kind of big thing that we need to sort of focus on in a standard library. The current test driver is, was starting out was just the project make file. You run make test, and it runs a bunch of tests and says, great, it works. I've added some initial support for CMake and CTest, but this hasn't been accepted upstream yet. And it's only testing runtime correctness at the current time, but there's all this language in the standard around things that say, shall not participate in overload resolution unless, and that requires that we also have a test driver that can deal with things that fail to compile as valid test cases. And this still really doesn't mesh well with a simple make file unless you're willing to write your own testing framework in make. Further, both libstdc++, we use automake and Deja GNU as our testing framework, and libc++ uses lit from the LLVM project as its test driver within CMake. So ultimately, if we're going to incorporate this into a standard library, we'd like the test to run as part of the library's existing testing infrastructure. So one of the things in talking with Intel, we've decided to restructure the test to conform to libc++'s convention. It's sane, thanks to Marshall. Thanks to Howard. And the upstream project has now agreed to start using CMake and lit as their standard test driver. All the tests will be permissively licensed, which will hopefully encourage additional contribution to the test coverage. And then I have a separate bit of work that I do, which I'm trying to automate, which will pull these tests in from the standard structure that libc++ outlines into the existing test suite within GCC. And hopefully, at the end of this, we'll end up getting, ultimately better test coverage by being able to share those tests between standard libraries. So something that has recently, thanks to JF's work, come to pass is that Intel have agreed to donate their implementation to the LLVM Foundation. The idea here is that no one company owns it, no one company has any particular advantage. The LLVM Foundation is probably a better long-term steward in general of the code. And again, we want to see this code shared ultimately, I think, between libstdc++ and libc++. So this makes the most sense. There has been a little bit of delay recently trying to finalize specifics of licenses. I think that'll all get resolved in the next few weeks, and this will all move to the LLVM Foundation. And if you want to contribute, you can contribute according to the normal contribution guidelines of the LLVM Foundation. Hooray. So, but my main focus is GCC. So where are we at with GCC integration? There's an initial version that's done. There's been a request that's been forwarded to the GCC Steering Committee, which is awaiting approval to adopt the implementation. I have simultaneously submitted a patch request to my coworker, Jonathan Wakely, who's like the primary reviewer for patches to libstdc++. It was like a 15,000 line patch, so it's going to take him a while, I think, to do due diligence on it. Plus, there's still some flux as to what the specific license is going to be, so chances are I'm going to have to resubmit all of this again in the next week or two. But ideally, within the next few weeks, this should get accepted upstream, and you should be able to grab a version of GCC that has support for this in it. And if you can't wait that long, and if you're brave, you can go and grab some unofficial bits at this link and go play with them. And again, if you've got feedback, if you do that, please send it to me. But the current implementation is dependent on, that is really distracting, third-party a third-party library, specifically Intel's thread building blocks. And it's fine for an experimental feature, but ultimately we don't want to make GCC dependent on TBB. But I think preserving TBB support is important. There's code out there that uses it, and it would be nice to have that code compose well with parallel algorithms if you want to start adopting parallel algorithms within it. So our short-term plan is to go ahead and ship some GCC 8 point release. I don't know exactly which point release that will be. We'll mark the features as experimental, and it'll be dependent on TBB. And so if you want to use it, you have to use TBB. The long-term plan, somewhere between GCC 9 and GCC 10, is to release a new parallel backend that is not dependent on TBB. Intel actually foresaw this need in their design of the library. So they have an API that they've outlined for what you need to do to replace the backend. There's 8 primitive algorithms that you have to implement, kind of the nature outlined here. So if you're willing to go and write that, you can write your own backend potentially for the library, although I don't think that we've agreed on any standardized way of extending the library. So you're definitely off the reservation, as it were, when you want to go down this route. This is, I think, mostly intended for implementers providing like implementation supported backends. And to that end, so if I'm going to write a new backend anyway, one question would be, should we express this in terms of the Executors work that we've been doing in SG1 over the last several years? And ultimately, is the proposal outlined in P0443, which defines Executors, and P1019, which defines how Executors integrate with algorithms, are those sufficient to actually implement a real implementation of those algorithms? And so it would be helpful to the standardization discussion, I think, if we, especially if we're targeting C++20, to answer the sufficiency question at least. And so in the work that I'm doing to start replacing the back end, I've started putting together a parallel an experimental implementation based on the PSTL upstream sources, but integrating a new Executors-based backend, and then sort of simultaneously writing an experience report for the San Diego meeting, sort of outlining what that actually entails. This will be the paper number in the mailing. It's upcoming later this month if you're interested in that work as well. And wow, I've got plenty of time for questions, sorry. Thanks. When I did this in the first dry run, I just let questions run throughout it, but Anyone? There's, I think, microphones up here too.
I've got one.
Oh.
Can you go back to that slide where you had the customization points that GCC defines for its backends?
Oh, this one, yes.
So I find it very interesting that even with the 4 that you put up there, you said there are 8.
Yeah.
Exactly one of those has an equivalent in the current Executors proposal.
Yes,
or the current proposal targeting 20.
Right.
Do you think that's a problem?
You can implement the others in terms of one-way execution, right? You don't necessarily need the bulk parallel 4 to implement a backend for this. TBB internally doesn't do it in those terms, right? It creates, a set of work tasks. It partitions up input and hands it off through the various algorithmic implementations that they have. And if we want to, I think there's value in the optimization hints that like bulk one-way give about the shape of the input. But that doesn't preclude me from making probably a less optimal implementation that just uses one-way execution. But you still have to write the algorithms in terms of one-way execution, right?
Yeah, I guess the less optimal was my question. Do you think that that is a problem long term? I mean, obviously this level of customization point, quote unquote, I mean, it's vaguely speaking, was chosen for a reason, and it is very clearly one layer above where we're targeting right now.
Absolutely. And I don't think that we've even envisioned replacing your own algorithm implementations yet, or these primitives, right? We've only talked about this is how you schedule the work. Okay. I think there's a bunch of discussion that we eventually need to have, I think, around execution policies and how you implement not just the parallel versions of these, but the vectorized versions of these for a particular vendor. Like, you know, the CPU implementation is going to want to do things completely differently than the GPU implementation. So I don't think we have had that discussion at any real depth in the committee yet. So, yes.
Hi, I have two questions. So the first one is if you played a bit with the different schedule policies using like different schedulers from TBB. And the second one is if you have information about the timeline for being merged into the LLVM foundation.
So there's two questions. One is whether I've played with the other scheduling policies that TBB provides. So then the second question is timeline for integration into LLVM, libc++, or libc++, right? You had two questions. First one was playing with other scheduling policies for TBB. The second one was what is the timeline for integrating this into libc++, right?
Yeah.
Okay. So for the first one, no, I haven't. I just use the defaults that Intel picks. You know, the assumption is that it's their implementation, and not only that, the lead developer of this library is the current lead developer for TBB as well. So I haven't really played around with that. My work has mostly been focused on just getting the functionality into libstdc. As for libc++'s timeframes, I can't speak to that. I don't directly work on that project. So I think it was in, huh? Yeah, go. There's a mailing list where you can follow along with that. CFE dev is a good starting point for that.
I was more interested about like the license. So I was going to change, and what's the time frame?
We don't know for sure.
Okay.
It's ultimately lawyers are involved. So, you know, once lawyers do what lawyers do, then we should have an answer for that.
Hi, I have a question from the application point of view. Is the application responsible for deciding what can be parallelized and what cannot be? Or library takes that responsibility?
Applications take responsibility for requesting the policy that they want. And really what you're basically saying is that if you say that this is okay to execute in parallel, that means you did all your due diligence in making sure that the functor that you supply in the call to the algorithm is capable of being run in a parallel context. That the implementation always has the freedom to decide at the end of the day not to run that in parallel though. It can completely ignore your request.
Okay.
There's no guarantee.
So thread safety and parallelizability is primarily application's responsibility, but whatever they indicate doesn't have to be honored by the library.
Right. I mean, it could well be that you provide a set of input that is too small to profitably spin up threads to work on. So you might as well just execute it in the current thread. I mean, you asked for it, but you didn't really mean it, kind of thing. Okay. So, and that's the implementation has that ability. There are several algorithms for which there are no parallel equivalents that would actually yield speedups. So those just delegate to the serial version, and you're done. So it always has to be a suggestion to the implementation, but it can't be a requirement.
Okay, thank you.
Hi, so another application side question. Initializing the PBV scheduler can be problematic, especially if you've got other libraries that are referencing the TBB scheduler.
Right.
Are there any considerations for that?
Not really. I mean, you can go and initialize the TBB scheduler outside of these algorithms. They create a task region within the scheduler that's set up and execute within that. But they'll just do default initialization if
So the standard library is not going to do any
nothing special. And I don't even know how the standard library could properly expose that. I mean, that's one of the reasons why I think it's great that the backend pluggability exists, but depending on like the initialization strangeness of various third-party backends for a standard library is probably not the position we want to be in long term. And so I think the longer term approach is just to replace that with you get the default scheduler, and it's whatever the standard ultimately says about how you can control that scheduler.
So there will be controls to set up scheduler parameters when you replace it?
Executors. We're lumping everything into executors. So the idea ultimately, I cited this P1019 paper. The idea there is that you take an executor, it has the properties that you want, and then you say, this execution policy on this executor, run this algorithm. And so that's the long-term strategy there.
Thank you.
Yeah. That's it. Anybody? Anyone? Oh, yes.
I have just kind of a more general question with the parallel algorithms. Who's the audience for this? Is the audience basically, as the number of cores are growing or the number of processing units in general are growing, and people who would like to get some improvement from their code yet aren't, the fine-tuning, tweaking type, is that the audience of this type of a feature?
I think that's the intended audience, but just naively trying to parallelize your code, as we know, doesn't automatically yield performance gains. So I don't think the fact that we have these standardized algorithms that we can choose parallelization or vectorization for guarantees that a naive user can make gains just using it. I think the existing cases where you would have used OpenMP in the past, maybe you don't use OpenMP now. This might compose better, with modern C++ than an OpenMP pragma-based approach. But it's probably the existing users of OpenMP that would likely use something like this, I think, initially.
I was hoping you'd have that for an answer, because that that would be what my expectation would be. And so now my follow-up is, is there going to be enough flexibility in an executor to allow those who really want control of the system? Or is this going to end up becoming some type of a feature in which really nobody wants to use it because you want so much control that you're just writing it on your own anyhow? Or if you use it, you're shooting yourself in the foot.
Yeah, I don't know how to answer that question.
I'll take my question off the air, or answer off the air.
Yeah. The executor's proposal is trying to define an interface that implementations can conform to, including your own implementation. So if you're happy with the algorithmic implementations, but you want to provide different underlying execution model for it, the executor's proposal should allow you to do that. If you're not actually happy with the algorithm implementations, you're still on your own. You have to go and provide a different implementation at that point.
It's okay. He mostly worked around the comment I wanted to make.
Oh.
No,
No?
it's
Okay.
fine. I had a comment I wanted to make, and you made most of it anyway.
Okay. Right. Yes.
Yeah, so what I'm interested is heterogeneous computations. So is there any assumption of this being like a homogeneous scheduling or?
Currently, the assumption is that this all runs on the host, right, in a homogeneous compute environment. I think the long-term goal here is to allow you to take an executor that represents your GPU and say, run my parallel transform reduce on that GPU. We are, I think, quite a ways away from having an implementation that will do that. It would be great if some of the GPU vendors would get involved in this effort, and so that we can start looking at like what would an implementation look like for the standard running on a GPU.
So I guess as far as like extensions for different computing blocks, they'll be in the executors part, not this.
Sorry.
If I can provide an extension to my own block or something like that.
You could provide your own executor for. That would be the ideal. Yes.
Okay.
I don't think we're there yet. So. All right. I think we're done. Thanks.